I've been up early this morning, 7:30 almost, my breakfast, read the newspaper, and we are ready. I thought this would be somewhat smaller than the other exercises, but it seems that we have to go through the same drill as before. I prepared by writing the definitions of theta sub A and theta super A. Where are they? Yeah. And the transformation formula, which I think we shall be needing. And we have a new theta function where we shall take the Mellon transform and use the transformation formula. And then finally, when we have the answer to part C of the problem, we can check the result from problem 5. So let's get into it. Now let's see, theta A is defined by summing over all the integers, so I will use this definition. And use the same trick as before. Write n as we sum over A, so it's in plus b and sum b goes from 0. Or is it from 1? It's from 1. This should be an A, I guess. It goes from 1 to n. And I goes from minus infinity to infinity. Now what do we do? Well, let's do nothing at the beginning. With this, and this therefore of course becomes chi of A. And here we can take n outside. So we are beginning to get something like this. sum over all integers plus a number, and chi of a outside, yeah. So we take out n, it's a good idea to divide by n. There we go. And the summation over I of chi of a, so we perform the summation over I, and that should be exactly theta a divided by n, evaluated at n squared t, and what should we get? N half sum over a chi of a, right. That was the first formula. Preparing for the problem, I looked up how we did it in problem, was that in problem 3, I think? And I started on the left-hand side, so let's do that again. And then applied the formula, which we proved in section 2, problem 9. I think it was x there. And what was that? Chi bar of a times g of chi. High. And then theta super t. And we introduce psi equals nth psi to an, and then psi of x is psi to x, and now we can apply this formula like we did in problem 3. So it was summation, well, chi bar of n, g of chi and then we have an n well, we'll see if I miss anything afterwards. Well, the sum over a, that just went away. Oh, we have done that by obtaining g of chi. And then the sum I know it's silly writing it again, but I need it. And this, all this, oh, and the half, that's theta chi of t. So I get g of chi theta chi bar of t. And that's exactly what I should get. All right. And now part 3. Well, so the normal procedure is to use these two results to get it. And let's try that. And the transformation for the theta functions we have up here. Minus it t to minus 3/2 theta a super a divided by n, and then the reciprocal guy, and now it's time to check the result up here. Chi of a theta super. Well, that's exactly what we have. So let's take the constant, the things not depending on a outside the sum. I'll want a little more room here. And that was g of chi theta of chi bar, and then we just need the t we have. Oh, that's the same, 1 divided by n squared t. And time to compare, minus I, there's no 1/2, and n to the minus second, get that, g and theta of chi bar, that's right. So I'm wrong about factor 2. Oops, that just vanishes there, so that's easy. And then the factor n. Oops, I see now that we have to have t to minus 3/2. I'll just write the n I have here. I know I'm rationalizing now, that's not very good. You see, when I use the transformation formula, then we have n squared t, so it must be n squared t to minus 3/2. So that's divided by n to the third. We should have that already here. So here it should be n squared t. I'll just correct that really. So that gives n to minus third. Let's just take it out here. And then we get the correct result. That was part A. To go to B, we need first to show that the Mellon transform is integrable, and of course for all s, so that requires that the integral, that theta is a function of fast decrease towards naught and towards infinity. So it tends to infinity faster than any rational function at naught and at infinity. At infinity, it's the usual suspect. When n is naught, it vanishes, so there are only the exponential terms. And then when we substitute by 1 divided by t, we get a polynomial t to polynomials, but a power function t to 3/2 here, times theta of 1 divided by nt, which goes like e minus c divided by t for some constant as t approaches naught. So that means that this function is well defined, and so let's call it, what do I usually call it? I call it m, I think. M of s is an entire function. And then we have to compute it as usual when it can be done. So let's do that. No, I like to sum only over the positive integers, and we exchange sum and integration as usual. And there are no problems here at all. And I just write the formula every time. So it's pi to minus s, gamma s, n. Now this is weird. No, that is what we should get. N to minus 2s. So that's the n from here, gives that minus 1. Oh, chi of n, I forgot. Was that the result? Indeed it was. So I feel that it's becoming routine now. That's very, very pleasant feeling. There is one thing. Oh yeah, that's where does this integral make sense? And as I see it, we just need the real part of s to be positive. Oh, when we are over here, it's still just positive. So this is where we can do the integral, And then this sum, of course, only makes sense if what we've got in here is larger than unity. Or is it larger than naught? Nah, it might be larger than unity. So that means s, the real part of s must be larger than 1 to write this as this sum. So all in all, I need bigger than 1. And what does it say in the problem? It says s larger than 1/2. Well, I don't get that. Never mind. And then we shall use the functional equation, the usual thing. See? So we make the usual transform. Or maybe that's the complicated way of doing it. Maybe we should make the use this transformation formula first, and then make the transform. Let's do that. That's the way they have. Now, what did that say? Yeah. So first the constants. Minus I divided by n squared. And then the g of chi. The integral t to minus 3/2 theta of chi bar 1 divided by n squared t. And now we make the substitution. This may be the better technique. And we already know. Oh yes. I'd like to make a linear substitution here. And then this becomes u, and this becomes n squared u. then we have to multiply by n. So s plus 3/2 minus I n to 1/2, no, s minus 1/2. And then this is L of chi bar of, and then it's 2 times this power so up here we got 2 times s minus 1, and s was this power. So it's 2 times s plus 3/2, oops, yeah, minus 1. There was another, I forgot pi to minus s gamma s, pi to minus and plus 3 minus 1. That's a little weird. I expected something like 2 minus 2s. No, up here it's 2s minus 1. Yeah. So what I've done up to now is that this ought to be equal to this. It does not quite agree with, or look like, what I got in, I don't know, it was problem 3 or 4, but I will stop recording and compare them and see if I can reconcile the two expressions. I went to problem 5 and found the transformation formula. And here we have to change the value of s so that it here becomes not s, but 2s minus 1. So we must substitute s with 2s minus 1. Doing that, I get this. And the left-hand side agrees nicely. The right-hand side, not so much. And then reading it through again, I realized something. And that's when changing variable, going to the inverse. Now where did I do that? I do that here, then it becomes t to minus s. So it's a minus here. And that gives a minus here as well as here. So that results in a minus here. And and here, and here, and here. So that's n to minus s minus 1/2 minus s. So it means s minus 3/2 minus s and minus s. So let's see how far that brings us. N to, so there's a factor 2 of minus 1 plus s, pi to 1/2 minus s, gamma to 1, and L. So that was right. So I need to be a little more careful with these two. Now n was squared. So that must be 2s plus 3. Minus 2s, so that means n minus s, one minus 2s. How does that? Minus 1 plus 2s. I get plus 1. Well, we get the right here, so it's not totally off. When this is right, they are doing something right. And then the gamma. It must be 3/2 minus s. Well, I'm still a factor off, not a factor, a little off, but I will stop it here. It's easy to see when one goes through it once again, and I don't know if we will be needing this later. I believe a little more in the result we have up here. But they need to be reconciled. So I'll look at it and maybe I'll write it in the comment, maybe not. I'm sure you can see it.